So I would like to take this opportunity to briefly show you INESC Microsistemas e Nanotecnologias, or INESC MN. So we are a private non-profit research and development institute established in Lisbon, Portugal, and we specialize in world-class research, advanced training, and service providing on micro and nano fabrication and microsystems based, of course, on our clean room facilities and laboratories. Here we have up to 8-inch wafer capability and structure definition with a minimum feature size of 30 nanometers. And we focus the majority of our work in ICT and health spintronics, thin film MEMS, biomems, biochips, microfluidics, and device and material simulation. So to know more about our activities, I invite you to visit our website at www.inesc-mn.pt, or whenever possible, visit us in Lisbon. We will be very glad to receive you here. So without further ado, I give the word to our moderator for today's session, which is Katharina Lorenz, from the leader from the wide bandgap semiconductors. So Katharina, the floor is yours.
Yes, thank you very much, Vanya, and thank you very much, Emilio, for accepting this invitation. It's my big pleasure to introduce you to Professor Emilio Nogales. Emilio has done his PhD in physics in 2003. Afterwards, he made a postdoctoral stay in the University of Strathclyde in Glasgow. This is actually where we first met, because we were both postdocs in the same European project. I was based here in Lisbon for my first postdoc, and Emilio in Glasgow. He got his definite position as associate professor in 2010 at the Complutense University of Madrid, and his research interests focus on growth and characterization of semiconductor nanostructures. And he will tell us today about the latest results on the gallium oxide photonic applications. Emilio, thank you very much for coming, and the floor is yours.
Well, thank you very much for the very kind invitation. Thank you very much for the very nice presentation. I hope that right now you can see the slides. Is it fine? Okay. So it is a pleasure also and an honor to deliver this talk at the INESC MN. The talk is entitled Beta-Gallium Oxide Nano and Microwires for Widely Tunable Optical Microcavities, and it has been developed by several researchers. In particular, it has been done in the framework of the PhD thesis of Manuel Alonso Orts, who finished it a few months ago and is currently working at the University of Bremen, and it was co-supervised by Professor Bianchi Mendez and me and myself. It was done in collaboration with Professor Martin Eickhoff in the University of Bremen. Here, okay. And also in collaboration with the group of Professor José María San Juan and María Luisa No in the University of the Basque Country. Let me give you first a short outline of the talk. I will start with a brief introduction on the material, beta-gallium oxide, and the idea of using nanowires. I will also talk about the optically active defects in micro and nanostructured gallium oxide, and in particular in one we will use in this talk, which is the luminescence properties of chromium ions doping beta-gallium oxide. And then I will go to the main part of the talk, which are the tunable optical microcavities, which have been designed, fabricated, and characterized to be working in the near ultraviolet and the near infrared ranges. And I will finish with a short summary. So gallium oxide presents 5 different polymorphs, and the most stable one in standard conditions is the monoclinic one, the beta phase, whose unit cell is shown here, and it presents 2 different sites for the cation, for gallium. In one of them, it presents tetrahedral symmetry, and in the other one, octahedral symmetry, depending on how the oxygens around it are placed. And it presents an ultra-wide band gap of nearly 5 electron volts, which makes it very special because even though it has such a wide band gap, it is still behaving as a semiconductor, and well, it presents that way several capabilities which are different from the rest of the semiconductors and the rest of the TCOs in particular. It belongs to the family of the transparent conductive oxides, the TCOs. In this kind of materials present a band gap which is above some 3.1 electron volts, so that their transparency range covers the whole visible range. And even though some of them present very wide band gaps or ultra wide, they still behave with moderate electrical conductivity, so that the applications are in this family of transparent conductive oxides for displays where transparency is needed beside the conductivity. So gallium oxide in particular presents this very wide transparency range, so that it can be used for ultraviolet detectors and other photonics applications, as I will show some of them in this talk. It also presents a very high chemical, thermal and electrical stability, which makes it very useful and very interesting for harsh environment devices. And beside that, it presents, it was shown some 10 years ago, that it presents a very wide, very high, critical electrical field of almost 8 megavolts per centimeter, which when it is compared with the materials, the semiconductors that are currently used for high power electronics, which are gallium nitride typically and silicon carbide, it presents a critical electrical field which is quite higher. So there is a huge interest right now on this material, specifically for high power electronics, as it can reach powers and situations and characteristics which can go beyond the standard current materials which are being used. Anyway, this is not the point of this talk. This is the introduction, because this is one of the facts that makes this material so interesting for many people right now. So the main applications of gallium oxide, as I mentioned, are high power field effect transistors, deep ultraviolet photodetectors, making use of this transparency in the whole visible infrared and part of the ultraviolet range, also as gas sensors. But in this talk, I will focus on its use and the development of nanoscale materials or nanoscale particles to be used in photonics. In fact, it has been shown just 1 year ago that gallium oxide can be used. It's interesting not only for high power electronics, but also for high power photonics, high power optical applications, as shown in this paper published recently in Advanced Optical Materials. In fact, if we go to the first papers, important papers on gallium oxide published in the 60s, they were focused on the luminescence, on the photonics applications of gallium oxide and its use as a transparent conductive oxide. So the first works were focused on this part of the research on gallium oxide, and in the last 20 years there have been quite several papers, very interesting papers, developing these ideas and focused also in the nanoscale range of ultraviolet photodetectors, which are solar blind, and they use the fabrication and characterization of solar cells based on nanostructures, and also the fabrication of complex nanoheterostructures. So the idea in general of nanowires, of any kind of semiconductor, is to obtain them usually from the bottom-up approach, and obtain devices or applications such as this one shown here in a radial variation of the composition of this nanowire, which resulted in a high electromobility transistor, or this nanowire with a homojunction, radial homojunction, in order to obtain solar cells based in one single nanowire in the group of Charles Lieber, or this tunable laser due to a graduation of the composition in this 2,6 semiconductor, or even these structures were intended in order to obtain Majorana fermions for quantum computing, which is now a bit controversial due to the last findings a few months ago. But anyway, there are many applications of nanowires, and we will focus on the use of nanowires based on gallium oxide. Here I show some results we obtained some years ago in order to obtain some kinds of architectures which could be modified by modifying the conditions of growth, of synthesis of these nanostructures. I will show later how they are grown. And we obtain several kinds of architectures of nanostructures depending on the precursors used for this synthesis. We obtain these kind of structures which are based on gallium oxide, just gallium oxide with some branches and a central trunk, or also this kind of nano heterostructures in which we can see a central wire of gallium oxide with crossed wires made of tin oxide, or also this kind of skewer-like of particle decorated nanowire of gallium oxide with particles made also of tin oxide. So these are some examples of the kind of nano structures obtained based on gallium oxide, which will not be the main subject of this talk. Anyway, the main subject, as I mentioned before, is the photonics applications. So just to remind you that I mentioned before that the transparency range of gallium oxide goes above 270 nanometers. So it goes to the deep ultraviolet, thanks to the very wide, to the ultra wide band gap of gallium oxide, even though it is still semiconducting. It presents very strong, very intense luminescence bands. One of them, the one which is usually obtained for nominally undoped or unintentionally doped gallium oxide, either bulk or nanostructure or whatever, is this ultraviolet blue strong band composed usually by these two bands, ultraviolet and in the blue. This is a previous report already showing this, which are usually related to intrinsic defects such as oxygen vacancies, which behave as donors, or gallium interstitials with oxygen vacancies, which behave as acceptors, or even some impurities which are considered essentially to be intrinsic because they are always there in parts per million and so on, which could also result in this luminescence band. So this is one of the main bands already always observed in the luminescence of gallium oxide. However, in 2000, the group by Miyata showed that if gallium oxide was doped with optically active ions, different optically active ions, such as transition metals, shown in this plot here, or rare earths, such as those ones shown here, the luminescence band could be tuned all through the visible spectrum, from the blue to the red and a bit of the near infrared. So this idea is very interesting, as it can be obtained a material, emitters whose luminescence can be tuned based on a single material doped with different optically active ions. We use that idea in order to dope nanostructures, nanowires usually, or microwires of gallium oxide with different optically active ions, some of them the ones that Miyata used, and some of them which they didn't, in order to show the same behavior in the nano scale, and also to extend by using, for example, gadolinium, which emits in around 310 nanometers, so in the ultraviolet, or erbium, which emits in the infrared, a very well-known transition, which emits in 1.54 microns around. So to extend the emission range of these nanostructures at room temperature. We will focus today in these two bands, the one obtained from chromium in the red-NIR infrared, and the one which is intrinsic for gallium oxide, as these two bands are broad bands, and we will see what is the advantage of using these broad bands in these structures. So this is the way we obtain the nanostructures. We obtain them by a thermal evaporation treatment within a furnace, which is shown here schematically. We have a flux of argon and increase the temperature up to some 1500 degrees. Sorry. Sorry. Up to some 1500 degrees. Here we have gallium oxide pellets on top of which we place the precursors, like gallium, metallic gallium, and in some cases other precursor, as is the case in this talk, because we have doped with chromium by adding here some powders of chromium oxide. And the structures are growing here. We see here this video, which is a macroscopic scale. This is 0.5 centimeters. And we see how there are lots of nanostructures growing on top of the pellet, which Katharina mentioned that it was something like a volcano growing along several hours. Well, there are really a huge number of nanostructures grown on top of this pellet. So these nanostructures are the ones shown here. We take some of them, place them on top of silicon substrate usually, and characterize the properties, or in this case, in a TEM grid. Well, here are some examples of the luminescence obtained from some of our early studies on this material. If we have nominally undoped nanostructures, we obtain this ultraviolet blue band, the one I mentioned before, very intense one. But when we dope them with chromium intentionally, we obtain this very intense red infrared band. And in fact, it is so intense that it can even quench, in certain conditions, the ultraviolet blue one, which is usually so intense. So this gives the idea that the red infrared luminescence is very, very efficient. The luminescence from chromium, I will just briefly introduce it because it is well known, mainly since the moment that the first laser ever made by Ted Mayman in 1960 was based in ruby, which is exactly aluminum oxide doped with chromium. And the lines which are lasing are the so-called R lines of chromium 3+, which is placed in an octahedral symmetry site surrounded by 6 oxygen ions. This is the configurational coordinate diagram, and we have the fundamental energy level, the 4A2, and these R lines are produced by the transition from the 2E level to the 4A2. Besides, there is this other level, which in ruby is quite at a higher energy than the 2E1, which is not observed in the luminescence at room temperature. But in the case of gallium oxide, we have chromium substituting gallium also in an octahedral site symmetry. So that the coordination is quite similar to that in ruby. So the so-called Tanabe-Sugano diagram, which was made for the energy levels of chromium in these octahedral site symmetries, can be used for gallium oxide. And it is representing the energy levels with respect to the crystal field strength, which is representing essentially, or is related essentially with the distance, that is the average distance between the chromium ion and the oxygen ions which are surrounding it. So in gallium oxide, this crystal field strength is smaller than in ruby. So the 42 level is quite closer to the 2E level 1. And this results in a quite different luminescence band at room temperature. At low temperature, the R1 line, the same as in ruby, is observed. But at high temperature, also the 42 level can be populated because the energy distance is not that much as in ruby. So it can be populated at room temperature, and then it results in this kind of luminescence band. There is a broad band due to the transition from the 42 to 4A2 level, which, as the minimum position of this level is in a different place than the minimum position of the 4A2 level, it needs to be phonon assisted. And this phonon assistance results in the breadth of this emission band, this luminescence band. We characterized some years ago this configurational diagram energy levels and the Juan-Ruiz factor and so on. I will just show here a simplified schematic. So the 2E to 4A2 transition results in this R1 and R2 lines, sharp lines, while the 42 to 4A2 results in the broad band shown before. This is what we obtain. And all this luminescence is due to the chromium ions in gallium oxide at room temperature. So how can we use this? Well, we observed the behavior of the microwires as waveguides. The refractive index of gallium oxide is around 1.9, so it is quite higher than the air surrounding it. And then luminescence, the luminescence light or the light emitted by luminescence from the microwire will be confined due to total internal reflection along the microwire. Part of it will be reflecting inside, and this reflection results in going forth and back the luminescence. And if we check the luminescence spectra of these microwires checked at the ends, exactly at the ends, local luminescence, photoluminescence, we observe these R lines, the broadband, and on top of the broadband we see these slight modulations of the intensity. If we make a zoom of this region, we see these modulations, and we see that there is a so-called free spectral range, the distance between two consecutive maxima, which is dependent on the length of the microwire. And in fact, if we check the free spectral range, this distance for several microwires, we see that it scales exactly as the inverse of the length of this microwire. So this behavior is exactly the expected one for Fabry-Perot resonances, which are due to reflections in the ends of the microwires. The problem here is that these modulations are very weak, and this is related to a parameter which is defined for optical cavities, which is called the finesse. The finesse is defined as the free spectral range, so the distance between two consecutive maxima, divided by the full width at half maximum of one of these maxima. This finesse is directly related to the reflectivity of the mirrors, in this case the reflectivity of the end of the microwires. And the reflectivity here is not expected to be very high, as it is due just to the contrast between the refractive index inside and outside the microwire. So the reflectivity here would be something like an 8% or a 10%. And if the reflectivity is not too high, the finesse is not that high, and then this is not very pronounced. So we wondered how we could improve this reflectivity. And this is the main point of the talk. We defined photonic structures, artificial structures, in order to tune reflectivity from the near ultraviolet to the near infrared by designing, fabricating, and characterizing these micro structures. The idea is here shown. It is based in the Bragg gratings, which can be used as tunable mirrors by defining a periodic pattern of refractive indices by using two different materials, two different dielectric materials, transparent materials, so that we define a lattice parameter for this periodic structure, and the dispersion relation obtained from this structure is shown here, which shows these regions of frequencies of the electromagnetic waves which cannot be propagated inside the grating. So that results in the so-called stop bands, frequency regions which present a reflectivity which is, in the ideal cases, nearly 1, and transmission which is nearly 0. And we use this idea to define them inside the microwires used as waveguides. The good point is that this position of the stop bands can be defined quite straightforwardly just by changing the lattice parameter of this structure, of this periodic structure, so that the central wavelength of the wavelengths detected by the detectors in vacuum can be tuned by changing essentially this value, this parameter here. Well, this was the idea to define to define here a periodic pattern by a focused ion beam, so that there is a change in the refractive index from that of gallium oxide to that of air, to that of vacuum, nearly vacuum. If we define two such DBRs in one microwire, and we leave here an unpatterned region, then the light which is emitted by the nanowire itself will be confined in the 3 dimensions for specific wavelengths, which we can define, we can tune. The way to define exactly the parameters of these DBRs is by using Fdtd simulations. We first roughly estimate where it should be by analytical calculations, but due to the complex geometry, which is nearly one-dimensional for the electromagnetic waves of the nanowires, we need to do detailed simulations. So we define the DBRs and obtain this kind of plots of the reflectivity and the transmissivity, which are essentially stop bands. Even though the reflectivity is not that close to 1 as when you have two-dimensional ideal DBRs. So in this case, reflectivity is not expected to be increased so close to 1. Well, the workflow is the following one. First, we characterize the nanowires and microwires, obtaining the optimum shapes, the cross-section essentially, and checking that the luminescence of the microwire itself is very intense. Then we design and optimize the DBRs with Fdtd simulations so that the stop bands are defined in the ranges where we want by taking into account the exact shape which has been characterized by scanning electron microscopy. Then the DBRs are fabricated in the collaboration, and we characterize the optical characteristics of the microcavities, checking that there is an enhanced tunability of the Fabry-Perot structures. And finally, we compare the experimental results with analytical models and the Fdtd simulations created in step 2. Here's an example. We see an intense red emission due to chromium doping of a microwire. We check the exact shape by tilting the image in the SEM in order to see what is the exact cross-section. And we implement this exact cross-section along with the DBR parameters in the Fdtd designer. Then we allow the system to simulate by allowing a short pulse to be propagating inside the microwire to meet the DBR, so that part of the pulse will be reflected and part of it will be transmitted, and also part of it will be scattered. So if we detect here with the system, with the program, with the simulator, if we detect the evolution in time of the electromagnetic waves of the reflected and transmitted, and we obtain the Fourier transform, we obtain here the reflection and transmission spectra. And we check that indeed by changing the lattice parameter, we can tune the position of the stop band in each microwire. So the main idea is to make coincident this stop band with the range of emission of the microwire. It can be in the red infrared if it is doped with chromium, or in the ultraviolet blue if it is nominally undoped. And the result of creating these DBRs and the emission from this position will be such modulations created on top of the broadband of chromium in this case. So here are some examples of actual microcavities created. This is the schematic. And here we have a detail of the DBR. This is one of the DBRs, this is another one, and this is the region which will confine the light in the 3 dimensions. In this case, the lattice parameter was defined to be around 520 nanometers. Well, we have here another example in which the lattice parameter is much smaller, quite shorter, and the nanowire is also quite smaller. In this case, the nanowire was doped with chromium, so the lattice parameter is defined in order to have the stop range in the red infrared, so longer lambda. And in this case, it is defined for a nanowire which is nominally undoped, so the lattice parameter is shorter, so that the stop range, the stop band is defined in the near ultraviolet blue. We also define the length of the cavity, of the region which is unpatterned, so that we can tune how many modulations are in a certain range. So the free spectral range between 2 consecutive modulations, and also the lambda in order to define the stop range, the stop band. The experimental setup we have used in order to experimentally characterize the luminescence properties of these microcavities is based in a confocal microscope, in which we have a special module in order to deflect the excitation point outside the detection point, the optical axis of the system. That way we excite the luminescence in a position within the microcavity, but detect the luminescence which is scattered from the beginning of the DBRs. This is an actual photoluminescence image in real color when it is chromium doped. And we see that the scattering is created in the beginning of the two DBRs, and this is the excitation point. So the advantage of doing this, exciting in one point and detecting in another one, is that the scattered light is mainly the confined one, while the light which is being emitted here is mainly unconfined. And this way we enhance the relative intensity of the modulations of the confined modes with respect to the unconfined modes. These are the spectra obtained, some of them. In green here, we can see the spectrum before creating any pattern, the broadband, we have already seen several times in the talk. And these are two cavities created in this very same microwire. So we see that it changes dramatically from this broadband to this sharp modes. And we can see that in the same in the same microwire, by creating two different microcavities with different parameters, we can tune the position of the maximum of the luminescence. So this is one of the possible applications. We can tune the luminescence from the very same material with the very same dopant. These are the other two examples in different microwires with different cavities, in which we see that here the width of the modulations of these peaks is quite smaller than this one. Also here, the distance, the free spectral range between two consecutive maxima is bigger, is wider or longer than in this case or this one, because here L was 6 microns and here it is 15. So we show here that we can indeed tune the luminescence properties by defining different parameters. And furthermore, we extended this just 1 year ago. I think the last year we published this paper. We extended this tunability from the infrared to the ultraviolet blue by making the best of this broadband emitted by a nominally undoped nanowire, where we can see that we tune these modulations from even 340 nanometers, even though they are slightly weak, up to 410 nanometers for different cavities in different nanowires. In this case, as I mentioned before, just by changing the lattice parameter. So furthermore, we can also analyze the polarization dependence of this spectra, just because there are several modes. The thickness of these microwires is big enough as to standing several modes. It is multi-mode. This can be analyzed in the framework of Marcatilli model, which I will not go that much into it. It is just a model for a kind of waveguides with rectangular transversal shape. And in this framework, we can obtain the parameters of the wave vector, the different wave vector components, so that we can analyze what are the longitudinal values of Kc just by increasing integers L, because this is just corresponding each L to one harmonic, upper harmonics, which are creating standing waves along this microcavity. So we obtain this way the dispersion relation for each of the experimental peaks, checking that indeed they represented just consecutive numbers when the dispersion relation is represented this way. So it fits quite well with with analytical models, the experimental results, when the microwire is wide enough. When it is nanowire, then this model starts to be not that well fitting, because it is developed for thickness bigger than the wavelength, essentially. Another point that we wanted to compare was the reflectivity, which the experimental reflectivity as compared to the simulation reflectivity. The experimental one was obtained from the finesse, as I mentioned before. This is defined by the free spectral range between two consecutive maxima divided by the full width at half maximum. This is quite straightforward to obtain these results, and that way we obtain the reflectivity for each peak here, for each couple of peaks. So the highest reflectivity obtained so far by us is around 80%, which can be improved, but it is more than one order of magnitude higher than the reflectivity when the nanowire is unpatterned, and we are working in order to optimize even further these results. They can be improved. This is the comparison of the experimental reflectivities obtained for different spectral regions as compared to the simulations. And we see that for this cavity and for these cavities here, we obtain reasonable comparisons. They fit quite well, taking into account that this is experimental and there is a quite complexity in order to define experimentally the parameters of the DBRs with some uncertainty. This is for the red-NIR infrared cavities, chromium-doped nanowires, and this is for the near ultraviolet blue cavities for nominally undoped nanowires. In this case, fitting is quite well, and as I mentioned before, especially in this case, reflectivity, which is at most 45% or 50%, can be improved quite further, and as I mentioned, we are working on that as we have room for improvement. But this is a demonstration that this idea can be used from the infrared to the ultraviolet. So just to finish, I will show the main ideas as a summary. I hope I have convinced you that we have designed, characterized, and fabricated optical microcavities based on monoclinic gallium oxide micro and nanowires, which can be used in order to tune the luminescence properties from a single material with one single dopant, in this case chromium dopant or nominally undoped microwires. So this shows that gallium oxide can be used as a single material based tunable emitters when we fabricate this kind of micro and nano, micro cavities based on the micro and nanowires, and that we have obtained this tunability in a very, very wide range from the near ultraviolet to the near, from the near ultraviolet to the near infrared. So with this, I finish. Just to mention, this is the place where I work, the Complutense University. Maybe some of you already know it. We are in Madrid, and this is the place where our faculty is, next to the sports area, one of the sports area in the Ciudad Universitaria, where it is placed. This is our faculty, in particular, a faculty of physics, and our laboratory, where most of this research has been performed, is in the basement, somewhere over here. We have several scanning electron microscopes, so the best place is a basement, so that there are not very many vibrations. We have also the confocal microscope, a spectrometer for photoluminescence and photoluminescence excitation, also the furnaces in order to obtain the nanostructures. And this is the people that forms the group where I work, the physics of electronic nanomaterials, which was founded by Professor Javier Piqueras, who is now emeritus professor, and is now being led by Professor Bianchi Mendez, one of the co-authors of this work, Professor Paloma Fernandez, and Professor Ana Cremades. And he is Manuel Alonso Orts. I mentioned that he is the main author of this work, but it was part of his thesis, and that's me. So I leave to say that I thank you very much for your attention and for the invitation. Okay, and acknowledge the funding agencies, very important, the Spanish ones, the European ones, and the United States Air Force Office for Scientific Research. So thank you very much for your attention. I will be very happy to answer if there are any questions.
Thank you very much, Emilio, for these very nice presentations. If there are questions, you can just switch on your microphone and put your questions. You can also put your questions in the chat if you prefer. While you are preparing your questions, maybe I start by doing some questions. Emilio, are you targeting any special application with these cavities?
With these cavities, well, some of the applications that would be very nice with the cavities would be to obtain, to start obtaining some gain corresponding to some of these resonances in order to obtain, well, a gain medium, and in the best of the cases, it could result in possibly in lacing It is not clear that lasing can be obtained with gallium oxide in particular, but it has been shown for sure with other oxide semiconductors, nanostructures, and nanowires in particular. So this is one of the targets that would be very nice, and well, still we need to do many things to show if it is possible or not. Another possibility is one that we are indeed exploring, and we have advanced with it quite a lot, which is the use as a sensor. In particular, it can be used as a temperature sensor, because with temperature is changing the refractive index of the cavity. So that results in a shift of the resonances that we have observed. And that shift can be used in order to assess the local temperature of the microcavity. So that's some of the applications. Another one would be emitters with tunable wavelength, but that's more open.
Okay, meanwhile, there is a question in the chat regarding the chromium dopant.
Okay.
Actually, I think there is a small misunderstanding here, but I will read the question anyway regarding the chromium implantation. At what energy of implantation did you maximize reflectivity without damaging too much the gallium oxide?
Okay. Well, we have in fact, in collaboration with Katharina, doped some nanostructures with chromium by ion implantation. But the structures I have shown in this talk were not doped by ion implantation. These ones were doped in situ during the growth of the nanostructures themselves in the furnace by placing chromium oxide powders along with the gallium precursor. So that way there is no damage, because the chromium is being included in the crystal lattice during the growth at high temperatures, and everything is relaxed and everything presents a quite high crystal quality. So we don't have too much damage.
Okay. Maybe I take advantage of this question. You don't dope by implantation, but you are forming the pattern with ion irradiation.
Yes.
Do you have problems with the surface properties of the patterns that you are doing by FIP?
Yeah, actually, that was a tricky point that our collaborators in the Universidad del País Vasco needed to develop, because in order to create these patterns with focused ion beam, they need to observe the microwire to obtain an image with the focused ion beam, being used as a scanning electron microscope, but instead of electrons using the ions. So that creates the damage, as Katharina was mentioning. And they finally, what they did was to reduce the maximum the ion dose for those observations, and just with one single image, they then just removed the ion beam until they created by focusing in just the places where the holes are created. They didn't obtain any more images. So there is for sure a reduction of the luminescence due to this damage, but they minimized the damage as much as possible. One of the problems here is that we used as a substrate a TEM grid, a transmission electron microscope grid, so that the microwires were nearly standing in vacuum, well, with air surrounding it. We didn't have any substrates such something like silicon, which would change drastically the simulations and the results and so on. So as we have the microstructures on top of this TEM grid, it's not possible to anneal the nanostructures after this damage created by the focused ion beam. When we are already developing this idea on different substrates, solid substrates, so that in that case, hopefully, we will be able to use ion implantation with Katharina, for example, if Katharina wants, and then to anneal, and then to anneal the nanostructures after ion implantation. But we need another substrate. Sorry?
It should be easy to just transfer the ready cavities to a different substrate. I say easy with nanostructures. Nothing is easy.
Yeah, nothing is easy.
But I think it's possible.
It could be done, and actually it could be done by placing the wires before focused ion beam treatment, placing them on top of silicon, let's say, and then creating the DBR on top of silicon directly. So that would be another idea. Mm-hmm. Because the parameters of the DBRs for sure will be different depending on the substrate we use. Sorry.
There are several raised hands. Professor Teresa Monteiro from the University of Aveiro.
Hello. Hi, Emilio. How are you? Thank you very much for your talk. It was very nice work. I just like to ask you if you can tell us something about the doping content. They are diluted samples or evenly doped?
They are not heavily doped. They are doped. Actually, one of the points of our thermal treatments is that we don't have that much control on the concentration, the final concentration. It depends on the temperature we use, and at some extent on how much chromium oxide powder we use and how close it is to the nanostructures. But usually the concentration is around 0.1 atomic percent of chromium.
So, and the patterns are always the same. You have tried to do with different contents, and the patterns are always the same? Yes,
because you mean if they could change because of some excess, I mean, some increase in the luminescence and then creating perhaps some gain or something like that? Or?
No, just trying to correlate with the effects of the chromium content on the luminescence, for sure. And you have a lot of different kind of centers in the same spectral region. So that's why I'm asking about if the patterns maintains or if there are any changes when you change the concentration of the dopant.
Yeah, we haven't seen changes, at least appreciable changes. The main changes are due to the reflectivity of the DBRs, but not to the way chromium ions emit. Usually the spectra we obtain from the chromium ions don't change that much. It's true that sometimes the relative intensity of the R lines with respect to the broadband changes a little bit, and that can be because there are different centers of chromium, but these are not so drastic changes usually.
Okay, thank you.
Thank you to you. Thanks to you.
And there is Vanya.
Yeah, thank you, Emilio. The talk was really, really nice. I'm wondering, what is the smallest size you can fabricate the wires, and the smallest features that you can actually impose in the
DBRs? Okay. Well, the transversal dimensions of the wires is limited by the wavelength of the light itself. If you reach a transversal dimension which is similar to the wavelength inside, which is smaller than in vacuum, but inside, if it is reaching this size, then the wave guiding behavior will start to spoil. And there will be diffraction limits and so on, and light will start to flow out of the nanowire, even though there should be, due to the refractive index, total internal reflection. But there is a limit, which would be something like 200 nanometers thickness or something like that. Okay, so that's one limitation. And then for the DBRs,
And Emilio, you cannot go to another part of the spectrum?
Yeah, sure. That's why one of the reasons we went to the ultraviolet is that nanowires can be quite smaller, because the wavelength is something like half that of the chromium emission, and then the nanowires can be nearly half the diameter than the ones used for chromium emission. Yeah, and that was part of the good points of controlling this down to the ultraviolet region for nominally undoped. Yeah, and the resolution limit for the focused ion beam, which I think was your second question, is, if I remember well, nearly 10 nanometers or so. So these holes that have been created in these structures have a lattice parameter of around 200 nanometers or something like that. So the holes need to be something like 100 nanometers, and then it is nearly the resolution limit they could do just something like nominally a line, and the thickness of this line would be in the range of tens of nanometers, because the thickness also is influencing the final resolution. If you have a very thin layer, you will have more resolution with the focused ion beam than if you have a thick one, because there is some piling effects or something like that. I'm not an expert, sorry, on focused ion beam, but it would be something like that. So in the range of tens of nanometers would be the smallest one.
And you mentioned one of the applications possible for these nanowires would be temperature sensors. So do you have an idea of the ranges of temperature they would work?
Yeah, we are checking, but they are in several hundred Kelvin range. So from cryogenic temperatures up to 100 Celsius, something like 400 or so Kelvin. We are checking that, and we are right now, but I can say that because we have seen that this system is stable in that range of temperature, and we see the shift of the peaks in those ranges. Hopefully we will publish that in not a long time. We are advanced on that.
Thank you, Emilio.
Thanks to you.
It's a question by Virginia.
Thank you very much for that very nice talk. My question was, have you tried to, or do you think it's feasible to have electroluminescence? Have you, or is this even a possibility with these nano and microwires?
Well, in principle, I think it should be possible. Electroluminescence was shown, I have shown some results by a Japanese group, which was Miyata group in 2000, and they showed luminescence when including several optically active ions all through the visible spectrum, and those spectra were electroluminescence. They were in thin films, but in principle, I think that if the right contacts are created in the two extremes of the microwire or the nanowire, in principle, the conductivity should result in, at some point, in electroluminescence. As I mentioned before, gallium oxide is quite stable for quite high voltages, and I think that actually Marco Perez, who works with Katharina, has tried to obtain these electric characteristics with high voltages, and in principle it's feasible. So I think that in principle should be possible, but we have not tried.
You said your temperature sensors are good to about 100 degrees C. What is limiting the functioning at higher temperature? It's just the quenching of luminescence, or?
No, it is the limiting point was the heater. We could not increase higher. In principle, gallium oxide is quite stable at up to 1000 degrees Celsius. We don't know if resonances would be there up to such high temperatures, but it could be possible to think that several hundred Celsius could be reached by this technique. We will see. We will see.
Okay, so it's just technical, because I thought it would be the ideal material for high temperature applications.
Yeah, okay, that's one of the main points that we wanted to show with that work. And well, maybe I'm talking too much because we still have to to publish. But yeah, no, we are searching for that actually.
Which brings me to another naive question. How did you do the film of your nanowire growth at 1500 degrees C?
How did we do what? The
filming of the
okay. That was done by Iñaki Lopez, who did his PhD thesis in our group. He defended it in 2014. And what he did was to place a photograph camera at the end of the tube of the furnace, which has a small hole, so that it is something like an exhaustor, so for the gas going out. So he placed there the photographic camera and took a picture every 1 hour or every 30 minutes, and then he added all these pictures to make this GIF video.
Okay, thanks. Because it's really a good resolution. I thought you really introduced something into the oven, but
okay, no, it was outside. I think, yeah, that would have been difficult because the temperatures in the tube, even though it is at the end, it could be several hundred degrees C. Yeah, he did it from outside. He managed. I don't know how. I didn't see how he did it, but it was amazing, this video. Nice.
Okay. Are there any more questions? No, this does not seem to be the case. I actually still have a lot of questions, but our time is already up, and I will see Emilio next week, and I can ask all my questions to him.
Okay, great. So thank you very much. I thank you all for the attention and for the invitation. Thanks a lot.
Thank you very much for the nice presentation, and thank you very much to everybody for assisting and being here on a Friday afternoon.
Thank
You
you.
have an announcement to do.
Thank you again, Emilio, for the very nice talk. So before we leave, I want to remind you that our next INESC MN student seminar will be on the 23rd of July and will be given by Tiago Pestana. And also one of INESC MN publications was selected by the editor of Micro Machines as journal hot paper since it was published. So check more information on our website. And as always, thank you for attending and have a great weekend. Bye-bye.
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 Thank you.
Bye,
Bye-bye.
Thank you very much. Bye.
Thank you, Emilio.